Welcome to The Explainer. Today, we're diving deep into the hardware of the mind. We're going to get real about the brain that evolution actually gave us, because to understand how we think, we first have to respect how we're built.
And this quote, well, this is basically our mission for today. We're not just going to list a bunch of brain parts. No, we're on the hunt for the fundamental design principles, the non-negotiable rules that our own biology sets, which end up shaping everything from what we see to what we think.
So here's our game plan. We'll kick things off with the brain's actual physical structure. Then we'll explore how it's basically a prediction machine, dive into the electrical rhythms that make it all work, look at the insane energy bill it racks up, and finally, see how all these so-called limitations are actually the biggest clues we have. All right, first things first, we've got to get our mindset right. When we talk about the brain's limitations, we're not talking about flaws or bugs in the system. Not at all. These constraints are actually powerful hints that point us directly to how the brain solves unbelievably complex problems.
I mean, think about it. This isn't some sleek computer designed from the ground up in a lab. It's an evolved organ cobbled together over eons, with ancient parts repurposed for brand new jobs. Its very architecture tells this deep, fascinating story about what kind of strategies actually work in the messy, unpredictable real world.
So let's get into that architecture. If you look at the brain's physical layout, its most consistent feature, by far, is its powerful multi-level hierarchy. And understanding this structure is absolutely key to figuring out its function. Okay, so the cerebral cortex, that's the wrinkly outer layer you always see in pictures, it's organized into 6 distinct layers. Now, the way these layers connect from one brain area to the next defines a really clear hierarchy. What's amazing is that this layered structure is remarkably consistent, whether you're looking at vision, hearing, or touch, and even across different species. That tells you it's got to be fundamental to how the whole thing works.
And this right here, this reveals the brain's fundamental asymmetry. Information doesn't just flow in one direction. You've got signals coming from your senses traveling up the hierarchy. We call these prediction errors. This is the surprising stuff, the news, the things that don't match what the brain expected. And at the same time, you have signals flowing down the hierarchy. These are the predictions, the brain's best guess about what should be happening right now. Now, if we zoom way in, we find this incredible, repeating pattern of wiring called the canonical microcircuit. The superficial layers, the ones closer to the skull, their job is to handle those prediction errors. And the deep layers, they're the ones generating the predictions. It's this beautiful little circuit, repeated over and over again, that acts as the neural engine for what we call predictive coding. It's constantly separating what we expect to happen from what's actually surprising. And get this anatomical fact is just stunning. The brain has at least as many connections for sending predictions down the hierarchy as it does for sending sensory data up, and in many cases, way more. This proves the brain isn't just a passive receiver, just reacting to the world. It's a system that is utterly dominated by its own internal model of reality.
So how in the world does the brain manage all this traffic, this constant conversation between predictions and errors? Well, it isn't silent. It has a beat. It has a rhythm. The brain's electrical oscillations aren't just background noise. Far from it. They're actually crucial computational tools.
And this separation creates something called a spectral asymmetry. It's a fancy way of saying that the two different streams of information, the errors and the predictions, use different radio frequencies. The fast, high-frequency gamma waves carry the rapidly changing prediction errors up the chain. Meanwhile, the slower beta and alpha waves carry the stable, contextual predictions back down. It's like they're operating on different channels to avoid talking over each other.
What this shows us is that the brain's hierarchy isn't just about space, it's also about time. Each frequency band is specialized for a different timescale. Gamma is all about the here and now, handling details within milliseconds. But the slower rhythms, like theta, they integrate information over hundreds of milliseconds, organizing individual moments into a flowing sequence, like an episode in a story.
So the big question is, how do these different levels actually talk to each other? The answer is something called cross-frequency coupling. You can think of a slow rhythm, like theta, acting like a conductor for an orchestra. It controls when the faster gamma rhythms, the violins, let's say, can play their part. This beautiful nesting of rhythms is how slow, abstract, high-level context organizes all the fast, detailed processing happening at the lower levels.
This all leads to an absolutely incredible principle. For two brain regions to communicate, it's not enough for them to just be connected. Their rhythms have to be in sync.
By simply adjusting these phase relationships, the brain can flexibly change which information highways are open for business at any given moment, and it can do all of this without physically building a new road. It's a ridiculously efficient way to route information.
Now, all of this complex, rhythmic, incredible processing, it doesn't come for free. Not even close. The brain is the most expensive organ we have, and it operates under a super strict, totally unforgiving energy budget.
I mean, just let that number sink in. This thing, which is only about 2% of our body weight, is hogging a full 20% of our daily energy. That incredible metabolic cost is one of the most powerful pressures that has shaped the brain's entire strategy for how to compute.
So, why is the brain a prediction machine in the first place? Well, it all comes back to this crazy energy bill. It is far more efficient to just run a model of the world, paying a small, continuous cost to predict what's coming next, than it is to pay the massive metabolic price of being surprised by everything all the time. You see, accurate predictions are cheap. Prediction errors are very, very expensive.
And beyond just the energy, the hardware itself imposes some rules. Neurons are kind of noisy, a little unreliable. There's no single central processor, no master clock coordinating the whole show. This messy reality means that strategies like probabilistic thinking and local decentralized computation aren't just a good idea, they're basically mandatory. And the brain's architecture supports them perfectly.
Okay, so let's pull back. We've looked at the brain's structure, its rhythms, its budget. What does all of this biology actually tell us? What are the non-negotiable, hard and fast rules that these facts demand from any theory that even tries to explain the mind?
Here they are. This is the list of clues that evolution has left for us. Any theory of the mind that's worth its salt can't just ignore this list. It has to be hierarchical. It has to be bidirectional and energy efficient. It has to explain the brain's crazy rhythms and its massive feedback design. These aren't just suggestions, you know? These are demands.
And this really is the key takeaway from our explainer today. The brain's architecture isn't random. It's not arbitrary. It is a direct, it is an elegant, and it is an unbelievably efficient solution to a really, really hard problem. How do you make sense of the world when you're stuck with the unyielding laws of physics and biology?
By really, truly understanding and respecting this wetware, the biological hardware we're all running on, we can finally start to get a handle on the mind's operating system. The biology gives us the clues, and next time the mathematics will give us the language to finally read them.